Hello everyone, I'm Nitin, and in this consensus video, I'll be discussing definition of consensus, properties of consensus, steps of a consensus algorithm, and fault tolerance in a consensus algorithm. So let's get started. Let's talk about consensus in real life first. Consensus is the most crucial element of decision making that occurs in every aspect of our life. Now let's look at an example. Suppose five friends are going out for a meal together, but they have different opinions regarding which restaurant to go to. First person wants to go to an Italian restaurant, second person wants to go to an American, third person wants to go to an Indian, fourth person wants to go to a Mexican, and fifth person wants to go to a Japanese restaurant. After so much argument and drama, they might agree on one restaurant. That means reached a consensus. And guess which one? Of course, it's Indian, as it's my personal bias. So let's make this example more democratic and assume three friends suggested an Indian restaurant and other two suggested Italian and Mexican. Now we can reach a consensus on the Indian restaurant easily based on the majority rule. I modified this example to resemble it with the consensus in a distributed system. Let's have a look at consensus in distributed systems. Just replace 5 friends with 5 nodes of a distributed system, and instead of restaurant, each node is proposing a value here. First node proposes a value of 10, second node proposes a value of 20, third node proposes a value of 10, fourth node proposes a value of 40, and fifth node proposes a value of 10. Now, all these nodes of the distributed system can reach a consensus on the value of 10 based on the majority rule. But this does not cover the complete definition of consensus. So let's look at the definition of consensus in distributed systems. A consensus is a process of reaching an agreement on a single data value by all honest or non-faulty nodes or processes. Even in the event of some faulty nodes, it should be noted that honest or non-faulty nodes participate in the consensus process. Let's dive into more detail on consensus in distributed systems and look at the properties of consensus. So, consensus in distributed systems is the process of satisfying the following properties. First, integrity means that each honest or non-faulty node only decide once in a single consensus cycle. In other words, no node decides more than once. Second, agreement means that all honest or non-faulty nodes decide on the same value. In other words, no two nodes decide differently. Third, termination means that all honest or non-faulty nodes eventually reach a decision. In other words, all the nodes decide on a result or output value. Fourth, validity means that all honest or non-faulty nodes decide on a value which must be proposed by the node. In other words, the validity property ensures that the consensus cannot invent an agreed value on its own. So these are the 4 important properties of consensus. Additionally, fault tolerance is another property which I will explain it later. To implement consensus in distributed systems, we develop a consensus algorithm or protocol which may normally employ the following steps to reach a consensus. Step 1, elect a leader. Step 2, propose a value. Step 3, validate a value. And step 4, decide a value. However, these steps are generic steps of a consensus algorithm to understand the bigger picture and may vary from algorithm to algorithm. Normally, a consensus algorithm or protocol requires one node to act as a leader to make decisions and coordinate with other nodes to reach a consensus. Therefore, a consensus generally starts with a leader election phase where all honest or non-faulty nodes elect any node as a leader. The process of electing a leader and its time span may vary depending on the chosen consensus algorithm. The current leader leads the consensus process until it is successfully working. If the leader crashes or is unavailable, then this leader election phase occurs again and another node is elected as the new leader. Suppose node 1 is still a leader and leading the consensus process. Before we discuss rest of the steps of a consensus algorithm, just to explain that distributed systems are fault tolerant, and this feature is provided using replication of nodes, more precisely replicated state machines. If you don't know what a replicated state machine is, then I can just explain very briefly in simple language. Replicated state machine means that multiple machines or nodes have the same state. In this example, it is simply a value, and all nodes run the same sequence of commands in the same order to transition into the same state. Means that all nodes or replicas have to be consistent, and that is why we need a consensus. So generally, state change has occurred when a client sends a request to the leader. Upon receiving the request from a client, the leader proposes the next valid value or state and sends it to all the nodes. Now all honest or non-faulty nodes receive the proposed value. Then they vote for it whether they agree on it or not. If all or majority agree on it, then it's validated. Just to note, here we are mostly considering the positive life cycle of a consensus process. Once the leader has received the response from all or majority of honest or non-faulty nodes, it decides whether to accept or reject the proposed value depending on the majority of responses. This agreed value is normally sent from the leader to the client. Again, these steps and associated actions may vary from algorithm to algorithm. In a distributed system, node failures are almost inevitable. Therefore, the consensus algorithm should be able to run successfully in the presence of faulty or malicious nodes and provide some fault tolerance. We can classify faults into two categories. First, crash faults, where nodes are faulty and have stopped working. Some consensus algorithms only deal with crash faults. Second category is Byzantine faults, where nodes are still working but sending incorrect information and are not cooperating in a consensus process. Some consensus algorithms can also deal with Byzantine faults. Let's look at the crash fault tolerance process. If a consensus algorithm is resilient against crash faults, then it can normally reach a consensus in the event of f faulty nodes if the total number of nodes are 2f plus 1 or greater. Let's have a look at an example. If f equals 3 means 3 faulty nodes in the system, then we need 2f plus 1 total nodes. That is 2 times 3 plus 1 equals 7. So this system can tolerate maximum 3 faults. However, this is a generic rule and may vary from algorithm to algorithm. What happens if 4 or more nodes are faulty in this system? Simply, it will not reach a consensus. Examples of crash fault tolerance consensus algorithms are Paxos and Raft. Now look at the Byzantine fault tolerance process. If a consensus algorithm is resilient against Byzantine faults, then it can normally reach a consensus in the event of f faulty nodes if the total number of nodes are 3f plus 1 or greater. Let's have a look at an example. If f equals 2 means 2 faulty nodes in the system, then we need 3f plus 1 total nodes. That is 3 times 2 plus 1 equals 7. So this system can tolerate only 2 faults. Again, this is a generic rule and may vary from algorithm to algorithm. Examples of Byzantine fault tolerance consensus algorithms are DLS and PBFT. This concludes my presentation, and thanks for watching my video.